Hello, and welcome to the beginning of Unit 12, which is also happens to be the beginning of Week 6, I believe, of digital learning, which has been good, clean, family fun for all of us. So let's kind of get into Day 1, which happens to be why substances will dissolve in solutions. So some things we need to bring back that you should be able to know how to do. Should be able to know how to identify a covalent versus an ionic compound. You should remember your polyatomic ions. We'll talk about that in the future. You should be able to know how to write chemical formulas for ionic compounds using the crisscross method, and the covalent compounds using the metric prefixes. You should be able to know how to convert from mass to moles and moles to mass. We should remember the different intermolecular forces of attraction. That would be London dispersion forces, dipole-dipole, hydrogen bonding, and then also the ion-ion interactions. You should remember how to balance chemical equations, and you should be able to draw bomb diagrams, which is one of the things that we're going to spend some time doing as part of this lecture. So, some things we need to define. When we talk about a solution, the solution is sort of a term. It's a catch-all term in the real world, but in the chemistry world, it's a very, very specific definition. And a solution is basically when you have something dissolved in something else. But there are two definitions that you need to keep track of. So the first one is the solute, and the solute is the substance that gets dissolved. So it would be like, for example, sugar, if you were making Kool-Aid, or salt, if you were dissolving salt in water for salt water. So it's the substance that gets dissolved. Usually it's a solid, but not always. And then solvent is the substance that does the dissolving. So in like Kool-Aid, the solvent would be things like water. And in like salt water would also be water, but sometimes things don't dissolve in water, and we'll talk about that in the future. And another common solvent would be something like alcohol, like rubbing alcohol or acetone or something like that. So solute is the thing that gets dissolved. Usually it's a solid, not always. Solvent is the thing that does the dissolving. A lot of times it's water, but also not always. So, speaking of sugar, and Kool-Aid, we have to go back to how covalent compounds, what's special about them that makes them unique compared to ionic compounds, and that determines how they dissolve. So we have to remember that covalent compounds are held together by intermolecular forces of attraction. Okay, so in this case, I see the structure for the sugar molecule. This is a really complex sugar. This is the one that you would eat in like making Kool-Aid and things like this. So first of all, because it's a covalent compound, I know that the intermolecular forces of attraction here are going to be London dispersion forces. I see that another thing that is important to kind of note here is that these points are also where carbons are. So a lot of times in organic chemistry, we just don't draw all the carbons. We just draw them as points to make our lives a little bit easier. We should also note that there's probably going to be some dots, around these guys here. And a lot of times in organic chemistry, we just kind of negate some of that or forget to do it. So first of all, there's definitely London dispersion forces because it's a covalent compound. Also, I see that there is carbon bonded to oxygen, so there's going to be intermolecular force, an electronegativity difference that's going to be dipole. So there's also dipole-dipole. And then because the oxygen is bonded to a hydrogen, like in this instance here, I would say that there is definitely going to be hydrogen bonding. So that means that this molecule, it appears to me that it has a lot of things going on. And sugar, molecule polarity in this case, let's see, I see on the right side, I see 1, 2, 3, 4 instances of hydrogen bonding, and on the left side I see 1, 2, 3, 4 instances of hydrogen bonding. I also see 1, 2 places where we could probably see some dipole-dipole interactions, and then the dipole-dipole in the middle, here and here. So this looks like it's pretty much a nonpolar molecule. It's pretty symmetrical. And because it's a nonpolar molecule and pretty symmetrical, we do know that it does have some hydrogen bonding, some dipole-dipole, and some LDF. But to make our lives easier when drawing structures like this, a lot of times we will just say that the carbon, for example, might be a square. The hydrogen could be a triangle, and the oxygen could be a circle. And so because that's such a huge, giant, ridiculously large molecule, I'm not going to make you draw all of those things because I feel like that's a lot of work. So I'm just going to simply draw one square, one triangle, and I'm going to draw one circle to indicate that I have a covalent molecule. And that's all that we really need to draw for a little larger ones. The smaller ones will get a little bit more in detail, but for the big, huge ones, that's how I would draw the sugar mom diagram. And if it was a solid, in this case, if it was a solid, I would have it probably stacked a little bit like this. I would make a couple of them, and they'd be stacked, sort of something like that. And then maybe we would have another one here. And we're just making some type of repetitive structure, because again, if it's a solid, it's going to have some pattern to it. So that would be my mom diagram for sugar. Oh boy, got a little water. Water has a Lewis structure. We know that oxygen has 8 valence electrons, has 6 valence electrons. So I would draw something like this. And hydrogen has 1 valence electron. So I would draw something like this. I would draw my bonds here. And that would be the water Lewis structure. I know that this is a polar molecule because the electrons are centered on the central atom, and there's an unequal distribution of electrons. That unequal distribution of electrons comes from the fact that oxygen is significantly more electronegative than hydrogen, and as a result of that, the electrons are being drawn in towards the oxygen, and then you also have the unshared pairs of electrons here and here, and those create that unequal distribution, so that makes it a polar molecule. The intermolecular forces that we generally say are present are the London dispersion forces, because it's covalent, and hydrogen bonding. One might put down that it's dipole-dipole also, and that is true, but because hydrogen bonding is technically a stronger form of dipole-dipole, we generally omit that. So if I was going to draw my water molecule, I would say that H would be a triangle again, and O would be a circle again. So I would draw a bunch of molecules that look like this, and maybe bonded together, and then I would draw another situation up here. Oops, that's a little carried away. And then I would have my intermolecular forces of attraction, something like that. So I really want to know where my positive and my negatives are. So I would probably indicate that this is delta positive, this is delta negative, this is delta negative, this is delta positive, and make sure that they're interacting in that way. So we call water the universal solvent because water tends to, even though it's covalent, it tends to dissolve things that are not covalent as well. So it can dissolve ionic compounds, which we'll talk about in a minute, and it can also dissolve most covalent compounds because of the hydrogen bonding. So water tends to dissolve almost everything, and in the rare instances that it doesn't dissolve almost everything, we use something else like, say, an alcohol, like acetone or rubbing alcohol. So in order for sugar to dissolve in water, we have to have the same set of intermolecular forces present. So because sugar, as we discussed a little bit earlier, had LDF, had dipole, and hydrogen bonding. And water has LDF and hydrogen bonding. The fact of the matter is that because there are instances where the same intermolecular forces of attraction are present, that means that they can dissolve. So one of the phrases that I tend to use is like dissolves like, meaning polar molecules dissolve in polar solvents, and nonpolar molecules tend to dissolve in nonpolar solvents. However, because sugar has so much hydrogen bonding on it, and water is hydrogen bonding as well, we would then say that sugar is kind of a weird anomaly where sugar, because of the hydrogen bonding that's present, will dissolve in the polar water. So there's always sort of like an exception. So if I said that we had sugar molecules that look like this, from before, what we would do is we would then go ahead and surround them with water molecules, which would look something like this. And I'm just kind of trying to do my best to make this a little bit faster. It's kind of hard though, because so much. So what ends up happening is that these intermolecular forces of attraction are kind of always doing the same thing. So they're attracting to one part of the compound over another. But what really ends up happening is, especially with dissolving, is that you will have these solute particles being completely surrounded by the solvent particles. So if the solvent is water, in this case, if the solvent is water, we see that the sugar structure is pretty much being surrounded by water. And I'm missing one. I should do that right here real quick. Really tiny one because I'm running out of room because I didn't think this through. But this particular sugar molecule right here is completely surrounded by water. And the way I kind of drew it was the positiveness of the hydrogen is being attracted to the whole thing for the sugar, and I just kind of surrounded it and take it away. So that's what happens with when solids dissolve in something, and in this case sugar. So like the water molecules or the solvent molecules come in, they form some type of intermolecular force of attraction, and then when they start to pull that solute particle, in this case the sugar particle, away from the sugar compound, the water molecules completely surround it. And so the water molecules completely surround it, and now it's completely dissolved. So it kind of, on paper, would look like it disappears, but it doesn't actually disappear. It just is one big pile of sugar molecules is being broken apart into individual sugar molecules instead of a lot of them, and then we can't see them. So hexane is C6H14. Its Lewis structure would look something like this. 2, 3, 4, 5, 6, and we'll say and because hexane is a pretty big structure, we'll draw it a little easier when we draw the Mom diagram. But this is definitely a nonpolar molecule that really only exhibits LDF. So because it's a nonpolar molecule and because it really only exhibits LDF, it will not dissolve in water. So the answer to that would be a hard no. And it will not dissolve in water because nonpolar molecules do not dissolve in polar solvents as a rule, except for sugar. But remember, sugar had LDF and it had dipole-dipole, so it definitely, even though it was a nonpolar molecule, definitely had some intermolecular forces of attraction that would allow it to be dissolved by water. So hexane will not be dissolved in water. It will form a layer. Now, remember, ionic compounds are held together by ion-ion intermolecular forces of attraction. And what that really means is that the electrons are transferred from one atom to another to become an ion. So if we talk about iron 3 chloride, we might remember that iron has a Roman numeral 3, so it has a charge of +3. Chloride is Cl, so it would have a -1 charge. But when we crisscross the charges down, we really get the formula FeCl3. Okay, so what that would look like, though, what that would actually look like for us would be that, and I'm going to draw it down here, is that Fe would have 3 electrons, and chlorine would have its 7 electrons, and there'd be like 3 of them. And then there'd be that transfer of electron, and really what we'd end up with, as a compound itself, as a solid, we would have Fe, which would be +3, and then surrounding it would be Cl, 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 which would have all 8 valence electrons. Each of them with a -1. And they would have 1 of the electrons from iron. So that's what we really have there. But when we take these guys and we dissolve them in water, these ionic compounds, what ends up happening is the water molecules with the partial charge, so again, hydrogen, hydrogen, oxygen, has a distinct negative part and a distinct positive part. So what ends up happening with these water molecules is they will come in and they will pull the individual ions apart. So if I take iron, and I'm going to say that iron is going to be a square, and I'm going to say that chlorine is going to be, say, no, not a star. It's going to be, we'll make chlorine a heart. The way that I do this, which is different than Miss E and Miss Hum, is I will actually require that you put the charges inside these little boxes because I think that's important for much later understanding. So if I take and dump in, say, 1 or 2 molecules of iron 3 chloride, I would have something that looks like this. And then I would have like 6 hearts. And what I want you to really kind of focus on is that they're spread out from each other and they're not touching anymore. And then when we add the water with a partial charge, what really is going to happen is, and I'm going to draw these like this. Okay, so triangle, 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 yeah, triangle, triangle, and then circle, 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 and then other triangle, other triangle, other triangle, other triangle. And then, so note how the negative or the positive part of water is being attracted to the negative part of chlorine. And then when I look at the other one, the iron, for example, I would do something that looks like this, where the negative part of water is being attracted to the positive part of the iron. So that's what you really, really have to focus on. So like we could go back and we could fill in the water with X's like we did in the past, and that's important to be able to do and understand. But the big thing that you need to take away from this is that the positive part of water will attract to the negative ion of chlorine in iron 3 chloride, and the negative part of water will attract to the positive part of the iron in iron 3 chloride. Now, when ionic compounds are dissolved in water, they do what we call dissociate, and when they dissociate, what that means is they're actually breaking apart. So what I'm going to do is like write an actual equation for the dissociation. So if I said that iron 3 chloride, which we've already talked about, FeCl3, if that gets put into water as a solid, we get on the other side Fe, and we get Cl separated as aqueous, but we have to account for the fact that there's 3 chlorines and there's 1 iron. So basically we're just separating the compound apart into ions. Now, there's another example, calcium chloride. So calcium is a +2, and chloride we've already decided is a -1. So that becomes the chemical formula CaCl2. When that is a solid and that dissolves in water, it breaks apart into the calcium ion. Oops, this should be a +3. It should be a -1. And in the chloride ion, and it becomes aqueous. Okay, and then we have to go ahead and I balance this equation now. So I'm going to put a 1 in front of calcium, and I'm going to put a 2 in front of chloride, because that gives me the appropriate amount of ions on both sides. Then we also have sodium phosphate, and we know that sodium is +1, phosphate is the polyatomic ion PO4, and it's Na3PO4. And if I have solid Na3PO4, I'm going to produce sodium ion, and I'm going to produce phosphate ion, and these will be aqueous now because they're dissolved in water. They dissociated. And then I'm going to go ahead and balance, and that's all that's to it. So really you have to be able to know what the correct chemical formula is, and once you know what the correct ionic chemical formula is, you can then break it apart into its components. And that pretty much covers it. So if you have questions, please shoot me an answer. Otherwise, you do have a worksheet based on this that will help you walk through it. Thanks for listening.